Welcome back to lecture 14.1, where we are going to cover today basically chapter, like in Fin, we're going to do like sections 4.6, 7, 8, and 9. So 4.6 to 4.9. So basically we're going to talk about the Carnot efficiency. So let's call it Carnot efficiency. Okay. So what I mean is, last time we talked about heat engines, all right, and we drew this diagram of a thermal reservoir at a hot temperature, one at a cold temperature, and then had an engine in between. Right, we called this a heat engine, and we said that a certain amount of heat flowed in, a certain amount of heat flowed out, and we got work. Remember, we said that this was consistent with the second law of thermodynamics because not only did we get work out, but we also wasted some heat. And then we talked about that waste, and we said, well, for this process, right, our efficiency, eta, went like the work over the heat in, right? What did we want on top versus what did we put in? But our work was equivalent to QH minus QC. We did that very carefully last time. Or 1 minus QC over QH. Okay? So now, this time we're going to ask, if we don't know QC and QH, is there another way to characterize the efficiency? So to do that, let's look at our ideal gas. So when we have an ideal gas, last time we derived the fact, let me find where we did it. Well, we said, okay, that the Q hot, right? We actually did the Carnot cycle. Remember, we had our adiabats and our isotherms, and we went from A to B and B to C and C to D and D to A. And we actually were able to calculate what QH was, right? So we said QH was NRTH, and that was log of V. Let me just make sure it's VB over VA. VB over VA. And we said that QC was minus NRTC log, and this should be VD over VC. All right, so this one involves the high temperature isotherm, and this one involves the low temperature isotherm, where we moved from A to B, and here from C to D, along the isotherms. So if you don't remember, go back to lecture 13 point, I believe it should be 3 or 4, I forget, 13.4. Okay, so remember this was a change in definition of the sign convention for heat. Remember here we're saying that all heats are positive. This is a positive and this is a positive, and we have to determine whether or not it's flowing in or out, okay? So in this one we can switch this to NRTC or log VC over VD. Now, how can we go any further? Well, remember that along our, let me just draw our Carnot cycle. So remember we started at A, we had an adiabat. No, we started at A up here. We had an isotherm to state B, an adiabat to state C, an isotherm to state D, and an adiabat. So this was a TH and this was a TC. And these were our adiabats that connected them, all right? So this was VA, VB, VC, and VD. Okay, so now one thing we know is that we have a particular relation along our adiabats, right? So we know that our adiabats are going to start and end, for example, at TC and TH or TH and TC. And we have their volumes, so we can actually write down our equation for an adiabat, which was T1 V1 to the gamma minus 1 equals T2 V2 to the gamma minus 1. Okay, so let's do this one here, right? So we're going to start at, so let's imagine this adiabat. Okay, so we would say along this adiabat, we would get TH and VB to the gamma minus 1, right, at state B, equals, well, that's, we get to TC, and we're at VC to the gamma minus 1. And along this adiabat, we start at VTC, VD to the gamma minus 1 equals TH VA to the gamma minus 1. Okay. So let's rearrange. So what we're going to actually do is I'm going to, let's see, let's go and take them, let's take them right here. I'm going to rewrite this as TH VB gamma minus 1 equals TC VC gamma minus 1. So remember, this doesn't mean state C, this means cold, this means state C. Let's write TH VA to the gamma minus 1 equals TC VD to the gamma minus 1. All right, so what I'm going to do is I'm just going to take this equation and divide by this equation. All right, so we're going to take this one and divide by that one, and we're going to get VB over VA to the gamma minus 1 equals VC over VD to the gamma minus 1. Or VB over VA equals VC over VD. So now when we look back at this, right, we can say that our efficiency was eta was 1 minus QC over QH, right? Well, if we put in what those are, this is 1 minus nRTC log VB over VA over nRTH log VC over VD. Oh, but VC over VD is equal to VC over VB over VA. So this is simply 1 minus N. Well, let's get rid of our NRTs, so our NRs. So we'll just write it as TC log VB over VA, TH log VB over VA, right? So all I did was I subbed that in, and this is 1 minus TC over TH. Okay, so this is excellent because now we have our Carnot efficiency not in terms of the heats, but in terms of the temperatures. And it's very easy to know the temperatures in a particular process, right? So we're going to do an example in class where I give you a boiler. We'll do it next time. A boiler at a particular temperature and the cooling water and what's the efficiency. Okay. So that's pretty much how, say, the university makes its heat is with a boiler. So how efficient would the university heating system be? All right, now a couple of points on this are two things. One, this has a very, this eta, 1 minus Tc over Th. What are my units of temperature? Well, they're in Kelvin, right? So we said that this was always less than or equal to 1, and it could only be eta equals 1 if Tc was equal to 0. That is, if you have a heat cycle, right, where your thermal reservoir is at absolute 0, then you could have a Carnot efficiency of 1. But that's impossible to have a 0 temperature heat bath, so it's impossible to have a perfectly efficient heat engine. So you can see that the laws of thermodynamics and the efficiency of a Carnot cycle are really intimately related. Okay, so the one last question here is, I derive this for an ideal gas, but is this general or is this only applicable for an ideal gas? And it actually turns out that this is a completely general result. And you can think about this in terms of the following scenario. If I had if this only applied for the efficiency of an ideal gas, for example, but I had an equivalent to thermal reservoirs, right? So imagine I had a thermal reservoir and another thermal reservoir, and I had an ideal gas engine, right? So let's imagine that I have my ideal gas engine. So my heat flows, this is QH, and this is QC. And I output some work. But now I imagine, I had another kind of engine, right? Other engine, where instead of having it output work, I had it input work. So then I would have some heat flow in and some heat flow out. If this could be more or less efficient than this one, I could actually spontaneously generate energy, right? So we know that's not possible. So we know that the efficiency is identical for both, right? Because otherwise I could make energy out of nothing, right? I would have extra work or I would have extra heat. So that's not possible. Okay, so next time we're going to go on and we're going to talk about what an object like that might look like, okay?